equal technology partner, and this money would come through technologies. So let me go back how we used to work on the technologies. This is a case of a plutonium carbide fuel where nobody in the world had used this kind of a fuel because it's difficult to perform, difficult to recycle. So most of the countries like France, Russia, USA, Germany, they said India's fast reactor program is dead. This fuel is not going to work because we have seen that high plutonium fuels have not worked anywhere. So we had a challenge. At that time, we have Z80 kind of those of you who have age on their side would know that we were working with TDC 312, Z80, things like that. And we had to develop the image processing and the complete software based on stereology, where we could say that how this fuel is expanding, how the gap is closing, how it give a feedback to the fabricator people, would give a feedback to the reactor people. But this reminded us of Raman, who always said that there's a lot of power in the brain along with a lot of power with your equipment. And it is ultimately a combination of your brain power with the equipment power which makes you a winner. So coming to the energy story conclusion, that if you look at the overall resources, renewable, nuclear and all that, we have enough going. This country can provide enough electricity for good quality of life, and energy security is not something which is hypothetical story. Our resources without any imports should be able to provide all these resources provided we have our science and technology management in place. I must say that the story is incomplete. The story is not which is accepted by all the stakeholders, and this is one thing which we will have to complete in the coming years. Many mechanisms are there, people are trying, they would find that it is not true about India. Leave aside a country like Denmark, who says that give us 20 years more and it will be totally renewable. Why not a state like Gujarat or Tamil Nadu say that we would have no coal after 20, 30 years? I think it is possible, but I think we don't have long-term strategies where we would be able to work it. Coming to the water, water is something which uses all nano, micro and macro technologies. Whole lot of technologies are brought into play, and whether you are expert in the microfiltration, ultrafiltration, conventional filtration, reverse osmosis, biomicrobes or nanos, I think you have a place. And the challenge of the water, the clean water, we get clean water, we pollute it and then finally again try to clean it and all that, and we do many things. But the challenge of making a water available, which is enough in our country, with the technologies which are available and which would be developed, again if you say that is there a blueprint, is there a sizable resources, is there a sizable human resources development which would work in the human resources, how we are going to create that kind of a synergy, I think it is again something. But the way the things are happening, there are revolutions. There are revolutions as to how the micro systems, the macro systems and mega systems would be put in place in the coming years to be able to do that. The complexity of the machines is increasing. Sizes are increasing, the number of parts are increasing. In these, the materials are changing, embedded sensors and instrumentations are coming. And in a limited time period, when you want to sort of go ahead, how do you comprehend this system? No scientist or technologist or a group of scientists and technologists can comprehend all that. So you have to have very large databases. We have not learned how to create very large databases and use those very large databases. Very few of us have a capacity to create very large databases and to work on that very large databases. These require all very, very large databases, appreciation of the many of the disciplines. Only then you can be competitive in any of these complex technologies. So this is again some area where the technology gap is there and we have to do it. We have also a classical way of engineering, where conceptual design, product engineering, process engineering, manufacturing, maintenance, life cycle and all that would go. But you are trying to compress it to 20% of time or 30% of a time, and it is very clear that very large databases and disciplines would come into the play. Participation of academia, research and industry would be there, and it is not something which is not happening. It is already happening in very high performance technologies, and we have to really set up our system or the rhythm of our system or synergy to be able to do that. But I think if we take good initiatives, we take large initiatives, why we are so afraid of putting 200 crores or 500 crores into these technologies around a people, around the specialists who inspire us to do these things, we don't know. But I think with the Science and Engineering Research Board, there's a hope, there's a new baby in the court, and people feel that we'd be able to take decisions without bureaucracy, and we'd be able to move, we'd be able to identify people like it happens in all the countries. You identify the people and invest the resources in that person to be able to do it. And what I have learned all these 40 years is that some of us work in the concepts levels, fundamentals. We are very happy that a new concept is there. Great work, fundamental. We publish in high impact journals. Then there is a validation of concept, and that means it has to be accepted by many people who are knowledgeable in that area. It is not that you are talking about, people have to start talking after peer review that yes, this concept would grow. Then there is a laboratory where modeling, experiment, various things happen, and collaboration is still possible. In all these three domains, the collaboration is possible. Slowly you go to a component testing and collaboration is no longer possible. Technology comes to a stage where the money starts playing a great role. You have to do all on your own, and it is very expensive. So you must do the component testing, pilot plants, because without the pilot plants, you can't get the confidence if you have to invest in a huge way. And finally you come to demonstration, real systems and all that. So that means there are 6 levels of maturity which one has to cross. And many times, what I talked in the first slide, we have fragmented linkages. We have some people who are doing in each domain, but if you say that we have all that, except leaving aside the strategic sector to a limited extent, not fully successful, but to some extent strategic sector has put this game where they put from the concept. But till now, we were doing something, concepts and validation, which were done by the other countries. Only in the last 5-6 years, we have started doing technologies which nobody has done. We are saying that we do these technologies. That means we have to really know how to bridge these fragmented linkages when we go from fundamental concepts. We have to learn to respect the failures more, because when you go from your concepts to the validation of concepts, many things would fall. I think still we don't have a system where we are points, where we should have collaborations, where we should invest more, where we should give the human resources, and finally we have to deliver a robust technology. NASA has a different thing. They call it as a 9 levels of technology readiness levels, and it goes almost into the same, but it is a redefinition of many of the things. It is not much different than what we use as 6 levels of maturity, but it is also a sort of a basic technology research, research to prove feasibility. I think it's the same story, but you should have something like that to be able to do. What is more important, which we didn't do and which we should do, because NASA, most of the projects which they are now doing is a first of a kind. Exploration deep into the space, even the environment is not known. You don't know that what your system would have to face, how you would validate and all that. In that case, research, development and degree of difficulty, they define. In our country, we say research, development, deployment, demonstration. Demonstration and deployment. We also call RDQ. But they call is a degree of difficulty. And they classify 5th level of RDQ when R&D effort could lead to a success which is less than 30%. So they fund very heavily even those projects where R&D possibility to yield result is less than 30%, even after a lot of rigor. I think we are still, as we are going to new technologies, we normally are in 95 to 99, 90%, maybe sometimes we also fund 80% and all that, but still we don't have a mindset to say that a person comes and he says that you give me so much money and resources, I may succeed only 10%, but if I succeed, this would be the kind of a story and all that. Some people would do it, and most of the people find it difficult. My areas of pursuit have been these, and currently I am more interested in near zero friction coefficient and wear rate engineering surfaces and superhydrophobicity. Can I build superhydrophobicity into the material and manufacturing and try to see how to do these things. So I'll give you example that we did some work fundamental level. I'm just explaining with a few examples our 6 levels of maturity. Just looking at laser scattering, when the lasers became available, we said let us look at the laser scattering. And we could find that we could find very small, very small, even they can be called benign microstructural changes, and we could pick up scattering was markedly different. Even if you have a small change at the grain boundary, the scattering is very different. And grain boundary engineering is becoming very important. Then pits, crevices, they are responsible for large number of failures with disaster consequences. So we could develop the physics of it, we could develop the instrumentation, but real technology came when Sri Chitra was developing a heart valve. They have a disc which is made of advanced polymer. And without touching, you must find that it's a very polished surface, there is no roughness on this. Because if any roughness is there, blood would coagulate and that heart valve would cause problems to a patient. No technique was there, and nobody would talk about, because India with Professor Valethan was trying to do the first Indian heart valve in the country. So they came to know, and then we said that yes, we have some technique and we can try it. So we used this, but we used a lot of pattern recognition of the scattering signal, not as clear as I am showing you the example. I can't discuss that work because that work is really the basis of how we are sort of giving confidence that those heart valves are working. But using the same principles, finally we could say that yes, with TTK healthcare, we could install that system and say that. In the large structures, you are always not possible to be able to do the complete monitoring. So you must be able to do where the problem is originating. It is something like security people or the intelligence people, where really the problem is originating. Again, work over very large periods and all that. I'm showing just a fundamental work to make a case, just like in light scattering, that it is possible that under the given environment, if you monitor the temperature, you would be able to say where the problem is going to come and where the failure is going to happen, and you can image that. Then we said no, let us go to the doctors and try to see that whether we can help the people in the diabetic, vascular diseases, dermatology, rheumatic diseases, and we found on a very large number of cases, working with almost 5 or 6 hospitals, we were able to demonstrate to them that look, if you look with the particular protocol, with the particular way of doing the measurement, if you are able to do, you have the answers and very cost-effective answers to many of these problems, and you can really get confidence. And of course, all these need a lot of work on the sensors and looking at the conventional physical sensors, chemical sensors, mechanical sensors, finally going to MEMS. We could devise many systems where we could use it on the reactor, and here we collaborated with a large number of institutes, and finally ultrasonic transducer based micromechanical system would be used in prototype fast breeder reactor. And we developed almost 100 sensors ab initio to be able to give the answers to the measurements which were extremely important. Superquantum interference methodology to find the defects in the chips is very important. As you go to high performance, you don't have really good method to find small defects, and especially when you are playing with the new materials. So SQUID is again a very good method. We have been able to come to the macro SQUID macroscope, which I show you the example, but we have not been able to come to the micro level. But I think many technologies which we are now talking about would demand from us to take SQUID to a micro level or even below micro level. And this again one challenge which the group is undertaking. Of course, SQUID we used for medical. Some of the very rare things to diagnose, like left bundle branch block, the doctors, the heart specialists, cardiologists said that it is not possible, and many silent heart attacks take place because this kind of diagnosis we are not able to do. So we requested the patients to come out to Kalpakam because this is the only instrument, developed instrument, and we did the spatial distribution of the signals, and we were able to say and demonstrate to them. And now I think there are 4 or 5 hospitals which are really saying to us that they would like to go for SQUID based system. Of course, we did SQUID based for the brain, and we have been able to find many conditions of the brain. Again, there are 2 or 3 medical institutes, including Sri Chitra, the Bangalore Institute or Brain Institute in Gurgaon, who are sort of coming, and we have already built a sort of a gap which we can put large number of sensors, make the signal, do the inverse modeling. This again something just to prove the point that while very, very conventional instruments you are importing, large number of medical diagnosis instruments we import, whereas we can build the highest end of the equipment also. Now what is lacking? What is lacking from a concept to a delivery of technology which we should do? So I just would like to say that when I started my research, I was looking at dislocations. Professor S. Ranganathan, Professor A.K. Rao, Dr. Placid Rodrigues, most of you who know that they were my 3 guides. And I was working at dislocations, and the problem I chose was that when signals cannot be detected, it is very weak, how I can amplify the signals and still detect it and predict the dislocation behavior. So it was mostly the whole work was understanding the movement of dislocation. We went to precipitates, we went to deformation, and finally when the Kaiga dome failed, they asked us to use acoustic methods to find out whether the ring beam is in place. A ring beam has also damaged and we have to change the ring beam. If the ring beam had also to be changed, the technology problem would be very different as compared to not placing the ring beam. If ring beam is there, we have to only build the dome, and that's good. We can again sort of go ahead with the restriction. We took up a problem on the musical pillars of Hampi, that how our ancestors were able to design these pillars. We wrote the full physics of acoustics on that, prove it by method. We went to the old musical instruments and found that how the nodes from these musical pillars are comparable to the nodes which are there. We looked at a kidney with the acoustic microscope. What I want to give a message is that you can start at angstrom level. We all know dislocation is an angstrom level game. You can go to nanometers, micrometers. You can go to 20 meters. You can go to 100 meters. You can come back to biological systems. But science is not changed. I don't think that at any time there was any difficulty to be able to apply science. It was more that we needed the domain specialists to be able to come and form a team with us. So my message is that we must work across the domains if we want to validate our science. Otherwise our science is not validated. This is a case I would not explain. In the thermal methods also, we took a similar approach. We started at dislocation level, the Luder band movement in certain materials, which is again atomic level phenomena. Finally, we came to breast cancer. We came to the paintings. We came to the kilometers long distribution lines, and all over a scale of 10 raised to 12. So you can appreciate this law's application, and the sensors, instruments, and the engineering is at that level. Same is true about electromagnetic methods. We again started at dislocation levels. Uranium we have to find in difficult areas. This equipment would not be given by other people, so we could develop our electromagnetic sensor instrumentation, fly it out into the space and find out how it is there. Same electromagnetic we could apply into the squid of the brain, we could apply it into the number of cases. So I think it is possible to expand your canvas to a very broad band in your lifetime if you really collaborate across, and your science, you have a passion to apply for the technologies. You must be ready to see many failures when you apply your science to the technologies. Of course, the wireless sensors, it is becoming extremely important for our energy security, for our robots. Reactors for some system, for safety they would not accept, but again we have applied it on fundamental level in the lab, going to the reactors, and we have a very strong collaboration here with IIT, and we do that. This is something which, why I feel that virtual reality is a great thing. Prototype fast breeder reactor we are doing for the first time. Now there are places where in a 20 centimeter area, there are 10,000 components which have to fit with certain tolerances to ensure the performance. There is no way by which I can install these equipment unless I go through a rigor of a virtual reality. And I have wonderful people to be able to do that. Building this expertise, which was not there in a country, we could do the virtual reality platforms for a whole lot of systems, and finally now all these are installed. All that based on the virtual reality, finally we are able to install and do it. Current area, the ultra low friction, we produce the lowest friction surface in the world. It's an engineering surface. Then we studied as to why we are able to get, and we are able to see that in a micro system, we are somewhere able to produce graphite embedment at nano level, and that is acting as a lubricating surface. And otherwise, a high friction surface, you can convert to a lowest friction surface in the world if you understand this mechanism. And we gave a mechanism, and we were able to say that. And this was the mechanism. We talked about the dangling bonds. If the carbon dangling bonds are there, you have high friction. If you can passivate them with oxygen or with some environment, you have very low friction. And we sort of did, and I think 10 or 15 publications of good thing came. Then we got interested into superhydrophobicity, because you look at many applications, the engineering performance would be increased if we are able to do superhydrophobic surfaces. These models are there which are well known, and today it is accepted that micro nano with texture is needed along with air gaps or the gas gaps, which would be able to give the superhydrophobicity. This literature has been existing for many years, and a lot of fundamental work is done. It is also realized that you can build a coating surface, but when the coating surface goes, again you have a problem of the performance, because the original surface gets exposed. So can you build a superhydrophobic surface, and you have no difference, so that even if abrasion takes place, still the difficulties are not there. Many people have tried, including ORNL USA, where they have a silica deposition by thermal spray, and they are able to make a superhydrophobic surface. But these silica needle-like deposition can go away, and superhydrophobicity can be lost. What we have done in the titanium surface, where the microfouling is very high, giving it a mechanical treatment and the chemical treatment, we are able to increase the contact angle to something like 140 degree or so maximum, and we are in this range. And the bacterial attachment we have demonstrated can come down by 2 orders of magnitude, which is very good, because titanium have this difficulty of bacteria. It's a very good material, but bacteria in the ocean, that makes a lot of difference. 9-chromium 1 moly, which is a boiler material used for millions and millions of tons all over the world. Again, we were able to create micro nano structures, and we were able to get even a contact angle of 150 to 158 degrees centigrade. We have published this work just about 1 year back, including a sort of a common language communication in current science, and already this work is becoming a trend center anywhere. Nanofluids, our breakthrough came when we were able to measure this kind of a small force between the nano fluid particles, and we also established the stability of the nanofluids, that how we can make these nanofluids stable. And once we had learned how to make this fluid stable and use this effect of the brush-like structure to get the stability, we were on to the applications. And now we are talking about that you can have sashes. You can have sashes of 1 meter by 1 meter just spread on a surface. Magnetize that surface, and wherever there is a pit or corrosion or crack, you would get a change in magnetic field, and that would reflect. If you shine the white light on that, you would get a different color, and you can get the defect very easily. You don't have to go through a sensor moving around and all that. So coming from that fundamental work where we spent 20 years or so, we are able to do this kind of a work. And of course, then we studied the scattering, and we observed the extinction of the light at particular magnetic fields, and explained it with the help of the orientation of the nanoparticles. And also we demonstrated that we can have a very enhanced transmission if we can align the nanoparticles into these hollow tubes, and these hollow tubes have a charge inside, and we found that we can get a multi increase in the scattering, and that scattering can be enhanced. And this has a pattern in it. With every 20 gas change, there is a sort of a extinction and again recovery of the, and this can be used in certain devices. Thermal conductivity has been a phenomenon that with nanoparticles you can enhance the conductivity, but again if you look at there have been 2 different schools. One is the Brownian motion can enhance, another is that the alignment can enhance, and with the help of our nano ferrofluids we were able to say that we can get very high increase in the conductivity, and we explained it with the theory and again it attracted a good attention, and I believe that would have many applications in electronics and also in the nuclear industry. So we sort of have I feel for the young people when I talk to young people. Nowadays I talk to students of 5 years or 6 years also, much more than what I was doing. I think Buddha is a great teacher to me. He was more than a religious head, he was a good teacher. I think we have to learn to detach, because if you get overburdened with, like what I said in the beginning, that so much is to be done, and how much I'd be able to do? I'd be able to do very little. So I think it's better to detach, clear, balance, experiment, have the convictions in whatever we are doing, because ultimately we'd make a small contribution. None of us can make very large contributions. We would make small contributions, but those would be of much value to the world, and we would definitely achieve. There's absolutely no chance that we would not achieve. We would definitely achieve. But all depends on what is our commitment, how much we are able to practice discipline, how much we are able to form teams. This is again something which I learned all over my life. In fact, it became more and more sort of disturbing for me. There was a time when academics and ethics people, I thought they had a steering wheel. When I was growing up as a child, or when I was doing my science and technology, I always felt in a family or everywhere that the steering wheel was with the people with large ethics and academicians. But now what I see is the politicians, bureaucrats, economists is the biggest canvas, and they are influenced by business and public in good way and a bad way. But this steering wheel is almost disappearing, and which sometimes worries you. But how? In gatherings like this, we sort of have a way that we have a steering wheel, we have a role in a society. In addition to all appreciation what others are doing, we have a role in this. And I talked about things like energy sustainability concepts, did talk about environment. I didn't have a much chance to talk about equity, but it is very important. Our society can collapse if things are not done with equity. We don't have to shy away from wealth, but what we have to worry is the ecosystem for wealth generation and management. We are maturing, we have to mature, and to my mind, it is the ethics. Ethics I relate with the womb of a mother, which is very pure. Very rarely I have seen children who are not ethical. Very rarely I have come across, but very rarely I have seen. So I think all these solutions may come, but I think without this, this structure would collapse. So we must have a very strong component of ethics, and ultimately forget about everything which is important: products, policies, geopolitical realities, water, human resources, minerals, energy, the mindset of a nation, mindset of individuals and a mindset of a nation. I think if you look at any society which is doing well, any family which is doing well, any organization which is doing well, to me one classical difference is the mindset. So I think we have to have a mindset along with all these things to be able to provide the answer. Thank you very much.
I'd like to thank Baldev for taking not only his time off, but given the fact that I gave him less than a week to prepare for this. So that's an amazing accomplishment. Before we go on to the interactive session, I'd like to invite Professor Bhaskar Ramurthy to please give a small token of appreciation to Dr. Baldev Raj.
Thank you. Great.
On your behalf.
Thank you.
So the floor is open for questions. I mean, as was mentioned in the beginning, there is no boundaries for questions. So please, yes, Kamakoti. Yeah. The mic is right there so that everybody can hear.
So you have done a lot of experimentation, and many of your experiments have been taken to real field. Can you tell one instance where your laboratory agreed majorly with your field, and another instance where your laboratory failed with the field, and the reason for the success and the reason for the failure?
tell you the example that we were working on a reactor and there were leaks which we could see with the borescope, but we could never really access. Now, to find the root cause that why these leaks are happening only in a few tubes, are not happening in many tubes, and what is the remedy available to us, we did in the lab studies with the eddy current testing. And in the replica, you can take the optical replicas, rubber replicas, and then you can find out what is happening. So we thought eddy current, what we had read is multi-parameter affected, even a small wobble or distance from the surface of the material which you are measuring, it would have effect. But once our mechanical engineer, smart